Alright, first of all, let's have a look at the solutions to the homework of topic 11. Of course, selectively. We'll start from number 9. This question asks us to find the shaded area. Given angle AOB is 120 degrees, and the radius of that circle is 6. So first of all, the area of the circular segment AB equals the area of the sector AOB subtracted by the area of triangle AOB, right? Since sector AOB is 120 over 360 degrees, which is 1/3 of that circle, so we can easily calculate this area, which is 1/3 times r squared pi, right? Pi times r squared, and this gives us 12 pi, right? To find the area of triangle AOB, we can draw altitude OX of triangle AOB. Since OA equals OB, this altitude is also median and angle bisector. Therefore, AOX and BOX are both 60 degrees, right? And triangle BOX and triangle AOX are 30, 60, 90 degree triangles. Thus, we have OX equals OB over 2, which is 3, and BX equals AX equals AO times square root of 3 over 2, which is 3 square root 3, right? Hence, we have the area of triangle AOB equals 1 over 2 times AB times OX, and this gives us 1 over 2 times 6 square root 3 times 3, which is 9 square root 3, right? And therefore we know the area of the shaded region equals sector AOB subtracted by the area of triangle AOB, and that equals 12 pi subtracted by 9 square root 3, right? Alright, any questions? Okay, then let's have a look at question number 10. In the diagram at right, triangle ABC is an equilateral triangle with side length 6. So this length here is 6. Arcs are drawn centered at the vertices connecting midpoints of consecutive sides as shown. Find the area of the shaded region. Okay, the area of our shaded region equals the area of triangle ABC subtracted by the areas of sectors centered at A, B, and C, right? Since triangle ABC is equilateral with side length 6, we can easily find this area, which is 6 squared times square root 3 in over 4, and this gives us 9 square root 3, right? And we also know angle A is 60 degrees, angle B is 60 degrees, and angle C is 60 degrees as well. Each of our sectors is just 60 over 360, which is 1/6 of the circle, right? The corresponding circle. Each sector has radius of 6 over 2 equals 3. Since each has the center at the vertex of triangle ABC and passes through the midpoint of a side connected to that vertex, right? Therefore, each area, the area of each sector here is 1/6 times pi r squared. This gives us 3 pi over 2, right? Therefore, we should use 3 times 3 pi over 2 here. And this gives us 9 square root 3 subtracted by 9 pi over 2. That's the area of the shaded region, right? You have any questions? Okay, if not, let's have a look at the next one. Question 11. In the diagram at right, quarter circles have been drawn centered at vertices A and C of square ABCD. Given that AB equals 6, find the shaded area. Our shaded region is formed by subtracting triangle ABD from sector DAB, right? And combining this with the region that is formed by subtracting triangle BCD from sector DCB. These two regions are congruent, so what we seek is twice of a difference between two areas, which is area of sector DAB and area of triangle BAD, right? And we know that angle A is 90 degrees. AB equals AD equals 6. We find that area of sector DAB. Is 90 degrees over 360 times pi r squared, right? And this gives us 9 pi. And also we can easily find the area of triangle BAD, which is 1/2 of BA times AD, right? And this gives us 18. Then inserting these values gives us 2 times sector DAB is 9 pi subtracted by the area of triangle BAD, which is 18, right? So eventually we have 18 pi minus 36. All right, have a look at the solution here. Any questions, just let me know, okay? All right, no questions. Let's have a look at question 13. Okay, again, we have a shaded region here, which seems complex, but we could start by expressing the area in terms of pieces we can handle. We can do so by starting with sector A, B, C of circle B and subtracting pieces. Okay, first of all, let's draw some auxiliary lines first. We could connect point C to this point, and let's call this point as Y. We could also connect Y to point B. Then we have the area of the desired region can be expressed as the area of sector ABC subtracted by the area of sector YBC subtracted by the area of segment BY of circle C, and then finally subtracted by the area AX. Okay, let's call this point X here. Let's call this funky area AXB. Right?
Can you draw out all the sectors on the diagram, like maybe putting on colors, because I'm the confused.
Alright, so sector ABC subtracted by sector YBC and then subtracted by segment BY of circle C. This is this area here, right? And then last one we have subtracted by funky area AXB. AXB is this area. Then you get the shaded region here, right? Okay, so now let's calculate these areas one by one. So first of all, the area of circular segment BY of circle C. Segment BY of circle C equals area of sector BYC subtracted by the area of triangle BCY. And furthermore, because CB equals BY, it also equals CY, right? Each is a radius of a circle with radius BC. then we know triangle BCY must be a equilateral triangle. So we can easily find this area, right? So the area of triangle BCY can be easily calculated, and sector BCY can also be easily calculated, right? So let's write them here. So area of triangle BCY is 4 square root 3 over 4, which is 4 square root 3. Sector BCY is 60 over 360 times the corresponding area of the circle, pi times BC squared, which is 4 squared, right? So that gives us 8 pi over 3. Also, triangle ABC is 90 degrees. And this tells us that the area of sector ABC is 90 over 360 times pi r squared, which is BC squared, right? So again, that's 4 squared, and that's actually 4 pi. Okay, then we have the desired region. Put all these values in. We have the desired region is 4 pi minus 2 times 8 pi over 3 plus 4 square root 3 minus the last part, which is funky area AXV. So the last part is a result of subtracting sector BCX from triangle ABC, right? So that's the area of triangle ABC subtracted by sector BCX, right? And this gives us 1/2 of AB times BC subtracted by 45 degrees over 60 degrees times pi times BC squared. And that's 8 minus 2 pi, right? Therefore, we have the desired region. If you simplify this, you will get negative 4 pi over 3 plus 4 square root 3 minus 8 minus 2 pi, which equals 2 pi over 3 plus 4 square root 3 minus 8. Okay, have a look at the solution here. Let me know if you have any questions. Okay, in this question, we know that 6 miles equals 6 times 5280, which is 31680 feet. In each full revolution of a tire, the earth mover moves a distance equal to the circumference of the tire, right? So first of all, the circumference of the tire is 11.5 pi feet. Therefore, to cover this distance here, the tires must turn 31680 over 11.5 pi, which is approximately 877 times. Okay, any questions? Okay, the next question I'd like to talk about is question 18. So here we have 3 circles of radius 12 lie in a plane such that each passes through the center of the other 2. Find the common area to all 3. Find the area common to all 3 circles. Okay, first of all, let's label some points. So let the centers of the circles be A, B, and C to facilitate our discussion below. Since the circles all have the same radii, and each of AB, if you connect these points AB, BC, and AC, then each of AB, AC, and BC is a radius of the 2 of the circles, right? We have AB equals BC equals AC, which is 12. Therefore, triangle ABC must be equilateral, right? The area of the shaded region then consists of an equilateral triangle plus 3 congruent circular segments, which is here, here, and here, right? So each circular segment has an area equal to the difference between the area of a 60 sector of the circle and the area of triangle ABC. Therefore, we have the area of the shaded region equals the area of triangle ABC plus 3 times the area of circular segment AB. Or you could also say segment AB. So this equals the area of triangle ABC plus 3 times the area of sector ACB subtracted by the area of triangle ABC, right? And simplify this will give us 3 times the area of sector ACB subtracted by 2 times the area of triangle ABC. Because we know the side lengths of triangle ABC, and triangle ABC is a equilateral triangle, then we know the triangle has area 12 squared square root 3 over 4, right? And the sector has an area 60 over 360 times pi r squared, which is pi 12 squared. Then we have a 3 in front. And then the difference is 72 pi subtracted by 72 square root 3, okay? And remember, always verify result by give it an approximation. So pi is 3.14. Square root 3 is about 1.7 something. So this is a positive number, right? Therefore, your result might be correct. Or if you have a result like 72 square root 3 minus 72 pi, then you should immediately know this is not possible because this is a negative number, right? You cannot have area as a negative number. Okay, have a look at the solution here. Any questions, just let me know, okay? Okay, if you don't have any questions, let's see the next one. Well, next question requires a little imagination. Or for example, if you have 2 coins, you can also do the experiment, right? Have you done this at home? Have you tried this? 2 congruent circular coins, A and Z, are touching at point P. So let's suppose this is one coin. There's another coin here. Okay, that's just a copy and paste. I think it's much better. Okay, so this is the initial setup, right? We have a coin A here and another coin Z. This is the center of each coin. So A is held stationary while Z is rolled around it one time in such a way that 2 coins remain tangent at all times. How many times will Z revolve around its center? So if you let point on Z that is touching A initially be point P, well, let's suppose another point R is here, then when the coin has moved a quarter turn, for example, when the coin moves here, where is the point R and P respectively? Well, R should be here, right? So let's call this R prime. And where is your P? The point on Z that is touching A is the one that is 1/4 of the circumference of Z from P, right? So your P becomes here. So let's call this P prime. And the coin just turned this way. And let's call this D prime. This is a new position, right? So as we can see here in this diagram, in this quarter turn, P goes from being the bottom point of Z to being the top point. Therefore, it has revolved a full half turn about the center of Z, as Z is moved a quarter of the way around A, right? Okay, I'll just write it here. Around A. So after 4 of these quarter turns, P will have moved 4 half turns about the center of Z, right? Therefore, eventually we have Z will revolve. Z revolves twice about its center, right? Okay, have a look at the solution here. Let me know if you have any questions, okay? Alright, if no questions, let's have a look at the next one. 21. Okay, we have 6 120 arcs joined centered at the vertices of regular hexagon ABCDEF. Each arc connects two vertices of a hexagon as shown in the diagram at right. Given that AF equals 6, which means the set length of the hexagon is 6, find the total area of the shaded regions. Okay, so let's call the center as O. Then first of all, there are some equilateral triangles, right? We could connect each vertices to the center O. Then because it's a regular hexagon, we know triangle AOF, AOB, COD, DOE, and EOF are all equilateral triangles, right? The shaded piece of the diagram inside triangle AOF, for example, if we only consider this triangle here, if we consider this triangle AOF, then the shaded piece of the diagram inside triangle AOF is the result of removing the circular segment OF of circle A and circular segment OA of circle F, right? From triangle OAF. To find the area of the circular segment OF, we then can subtract triangle OAF from the area of sector OAF. So basically, we have the area of the circular segment OF of circle A equals the segment OA of circle F, which equals the area of sector OAF subtracted by the area of triangle OAF. Okay, since triangle OAF is equilateral, then we know its area is AF squared times square root 3 over 4, right? Which is 9 square root 3 over 4. Oh, sorry, which is 9 square root 3, right? And the area of sector OAF is 60 over 360 times pi r squared, which is pi times OA squared. And this gives us 6 pi. Therefore, we know the area of the segment OF of circle A, or segment OA of circle F, is 6 pi minus 9 square root 3, right? So the area of one of our shaded pieces is given by the area of triangle AOF subtracted by 2 times the segment, which is 6 pi minus 9 square root 3, right? And we know the area of triangle AOF is here. So eventually we have 27 square root 3 minus 12 pi. That's one of the shaded area. So our total shaded region consists of 6 times the one shaded piece. So the total shaded area equals 6 times this number here, right? And this gives us 162 square root 3 subtracted by 72 pi. Alright? Okay, have a look at the solution here. Let me know if you have any questions, okay? Okay, to make this more clear, I should make it up like this. So this is a segment area of the segment, right? Which equals the segment here and here. Right? Can you see that? Okay, next question is 22. Number of inches in the perimeter of a equilateral triangle equals the number of square inches in the area of a circumscribed circle. What is the radius of that circle? Okay, so we could let each side of the triangle be length S. Then the perimeter of the triangle is 3S, right? The circumradius of an equilateral triangle equals 2/3 an altitude of the angle. So drawing an altitude of the triangle forms two 30, 60, 90 triangles, right? Of which the altitude is the leg opposite the 60-degree angle, and the side of triangle is the hypotenuse. So if the side length is S, we know the altitude has length square root 3 over 2S, right? So the circumradius has length 2/3 times the altitude, which is square root 3 over 3S, right? So the area of circumcircle is pi r squared, which is pi times square root 3 over 3 s squared. And this gives us 1/3 pi s squared, right? And this must equal our perimeter. We have s squared pi over 3 equals the perimeter 3s, and we can know that s equals 9 over pi, right? Since s cannot be 0, therefore the radius of that circle is square root 3 over 3s, which equals square root 3 over 3 times 9 over pi, and this gives us 3 square root 3 over pi, right? Any questions? Okay, quarter circle are drawn centered at each vertex of square ABCD as shown at right. Given that AB equals 12, find the area of the shaded region. Okay, this problem is a little complex, so we could make use of the auxiliary lines. So you make use of this point here. So let's call this point X. Then if you let X be the intersection of arc AC and arc BD. Consider this region bound by AB, AX, and BX. Okay, first of all, let's connect some points. Alright, first of all, let's consider this shaded region here. The region bounded by segment AB, arc AX, and arc BX. So we'll call this funky region. Or funky area ABX. Then, as suggested by the diagram, 4 of these funky regions plus the desired area equals the whole square. Can you see that? Because there is another one here, right? Another one here, and another one here, right? So 3 of these funky areas plus the shaded region equals the whole square. Then let's try to solve the funky region ABX. This region equals sector ABC minus the region bounded by BC, BX, and CX. You see that? Again, this region equals sector ABC, which is this region here. Sector ABC is this region here. Subtracted by the regions bound by BC, CX, and BX. That means this area here, right? And since BC, BX, and CX are ready of congruent circles, triangle BCX is equilateral, right? Triangle BCX is equilateral. Therefore, the region bounded by BC, arc BX, and arc CX has a area that can easily be solved. The area of the circular segment is the difference between the area of sector CBX and the area of triangle CBX, right? Therefore, the area of the region bounded by length BC arc BX and arc CX, this region is okay. I'll just let's complete this. Funky area ABX equals sector ABC subtracted by, let's call this green region. Okay. Okay, let's write it in detail. The area bound by BC, arc BX, and CX. And this area can be calculated by BC squared times square root 3. That's the area of equilateral triangle, right? Can you follow me? Equilateral triangle BCX plus the two segment, which is here and here, right? Can you follow me? I'm not gonna write all the descriptions here, so please follow me. Plus twice of the segment, which is 60 over 360 times pi BC squared. That's the corresponding sector, right? Subtracted by the corresponding triangle, which is BC squared square root 3 over 4. And this can be simplified to 48 pi subtracted by 36 square root 3, right? Then we could use sector ABC subtracted by this number here to get the funky area ABX, which is 90 over 360 times BC squared pi minus 48 pi minus 36 square root 3, which gives us 36 square root 3 minus 12 pi, right? That's one of the funky area ABX. The area of the shaded region then equals the square ABCD minus 4 of the funky area ABX, which is 4 times 36 square root 3 minus 12 pi, and then eventually we'll get 144 minus plus 48 pi minus 144 square root 3. Did you get it? So have a look at the solution here. Any questions, just let me know, okay?
In the first sentence, isn't it like 4 funky ABS plus the shade area?
Yeah, sorry about there's a typo here. That should be 4, right? Not 3. Okay, 144 plus 48 pi minus 144 square root 3. That's the final result. And sorry, there's a typo here. This should be 4. 4 funky ABX plus the shade equals a whole square. Alright, if no questions, let's consider the last question. 24. The figure at right shows a quarter circle of radius 1 with A on arc BD such that angle AOB is 30 degrees. Angle AOD is 30 degrees. So we need to connect A and O first. So this angle is 30 degrees. What must the distance OX be such that the region bounded by AX, BX, and arc AB occupies half the area of the quarter circle? Okay, so well, in order to facilitate our discussion, we could let OX be number X, length be X here. To find the area of the region bound by AX, XD, and arc AD, we subtract AOX from the area of sector AOD. Okay, first let's find this area. Okay, again, let's call it funky ADX. This equals sector AOD subtracted by the area of triangle AOX. Okay, we know AOD is 30 degrees. The area of the sector AOD is very easy to calculate, which is 30 over 360 times pi r squared, right? Which is a 12th pi. And the area of the triangle AOX can be calculated in terms of x. So we don't know this number yet. That's 12 pi minus, don't know this number yet. Let's try to find the area of AOX. So to find the area of AOX in terms of x, we can draw altitude from A to OX, right? Draw altitude here. Let's call this point Y. Since AOY equals 30 degrees, we have AY equals 1/2 of the hypotenuse AO, right? Which equals 1 over 2. Therefore, the area of AOX is, triangle AOX is 1 over 2 times OX times AY, which gives us x over 4, right? So we could insert this value here. That's x over 4, right? So actually we should put it here. Then the funky area equals 12 pi. Funky area ADX equals 12 pi minus x over 4. This plus the area of triangle BOX must equal half the area of the quarter circle, right? The area of the triangle BOX can also be expressed in terms of x, right? So this is 1/2 of BO times OX, which is x over 2. And the area of the quarter circle is pi r squared. Okay, 1/4 of pi r squared, which is just pi over 4, right? So we have the following relationship. We must have pi over 12 minus x over 4. That's the area bound by the green curves plus x over 2 which is the area of these green triangles must equal a half of the quarter circle, which is a half of pi over 4, right? And then we can solve this equation. This gives us the length of x. So simplify this will give us a quarter of x equals eighth of pi minus 12th pi, right? And of course x equals a sixth of pi, right? So the distance of OX must be a sixth of pi such that the region bounded by AX, BX, and RKB is half of the area of the quarter circle. Did you get it? Okay, that's part of the question solutions to the homework of topic 11.